What we were discussing in the last class, electromagnetic
Fine,
waves, have we
fine.
introduced?
Yes, sir.
Okay, fine. Okay, so good morning, all of you, and welcome you all to this online session of electromagnetic waves. So we are dealing with module 5, and in today's session, we will be discussing about uniform plane waves. In the last class, we have observed that electric field and magnetic field are perpendicular to each other. So if this is an electric field and if this is a magnetic field, and these two are perpendicular to each other, say this is x coordinate system and this is y coordinate system, so electric field is in the direction of x and magnetic field is in the direction of y, and ex and hy are perpendicular to each other. Then the wave propagation of wave will be perpendicular to both the planes, that is in z direction. So the wave will be propagating in the z direction. And also we have learned from the previous discussion, this electromagnetic waves travels at the speed of light, and also electric field will generate magnetic field will generate electric field, and they complement each other and travels to the larger distance. Since E generates rate of change of electric field generates magnetic field, or you can say curl of H, and rate of change of magnetic field will generate electric field. So and these complement each other, and hence it travels to the larger distance with this velocity. So with these two properties of electromagnetic waves, I could say the waves can be used as the means of transporting information from one source to another destination. So I could use this electromagnetic waves to propagate or to transport information in the form of energy, and we will calculate this energy in using Poynting's theorem. We'll understand this energy of wave or power of wave, and this energy could be transmitted from a source to some destination, and this carries some amount of information in the form of energy. Okay, so electromagnetic field is said to be existing if all the four Maxwell's equations are satisfied. Remember, electromagnetic waves, EMW fields, exist only if it satisfies all the four Maxwell's equations. If it satisfies all the four Maxwell's equation, then you could say electromagnetic field exists. And what are the four Maxwell's equations? The first Maxwell's equation is del cross E is equal to minus dou B by dou T. This is due to Faraday's Lenz's law. All I am trying to represent it in point form of Maxwell's equation. Del cross H is equal to J plus dou D by dou T, and here this is obtained due to Ampere circuital law. It's modified Ampere circuital law, and this happens to be in time varying fields or time varying electric and magnetic fields, whereas del dot D is equal to rho V and del dot B is equal to 0. This is a Gauss law in electrostatic field, and this is Gauss law applied to magnetostatic field. So now we shall see about the concept called plane waves. So what do you mean by a plane wave? The wave in which both E and H field vector lies in a plane and phase is constant over a plane. I repeat, E and H vectors, E and H vectors lies in a plane and phase is constant. Phase is constant. So E and H are in the same plane and phase is constant over a plane, then it is called a plane wave. So you might be asked to derive or define what do you mean by a plane waves and what do you mean by a uniform plane waves. Uniform plane waves. So plane in which amplitude and phase of E and H are constant. Plane in which amplitude of phase vectors E and H, that is electric field and magnetic field, are constant. Are constant. We call it as uniform plane waves. So how I could represent those uniform plane waves on the graph or pictorially, you could see if this is a y coordinate system and this is z and this is x coordinate system. So now this is hy, that is magnetic field is in y direction, and this is electric field, and now this happens to be the direction, that is az. This is a direction of a wave propagation. Direction of a wave. So what are uniform waves? Uniform waves can be given as, say, if this is a plane, so if I take this as x coordinate system, this is y, and if this is one plane, and your magnetic field happens to be like this. So this is your magnetic field, and your electric field is in this direction. it is in x direction. And now you may consider another parallel plane. I could have copied and pasted. Have another parallel plane. These two are parallel planes. And again, you could have a similar kind of electric and magnetic fields. And this is Hy, and this is Ex. And this could be located on in three-dimensional coordinate. Now these are called as uniform plane waves. They are called as uniform plane waves. You could see this is a plane where E and H, amplitudes of E and H vector are constant, and phase is also constant. And you could see this uniform plane wave traverses in the z axis. You can have another plane here. Okay, you can have another plane here in terms of electric and magnetic field, and this is how the wave propagates in z direction. So we have a general wave equation. You need to remember this general wave equation given by, please make a note of this, general wave equation. I will represent it in metric form. Okay. General wave equation is given by, I'll not be deriving this. You just need to memorize this equation. Del square E d h b is equal to mu sigma, its conductivity, over dou by dou t of E d h and b plus mu epsilon dou square by dou t square of E d h and b. So this is a general wave equation, and in phasor domain, this is in time domain or in frequency domain. Similarly, in phasor domain, you can write the wave equations as del square E minus zeta square E equal to 0, del square H minus zeta square H is equal to 0. Where zeta square is equal to propagation constant given by j omega mu sigma plus j omega epsilon naught, and this is called as propagation constant. Remember this wave equation? Del square E is equal to mu sigma dou E by dou T plus mu epsilon naught, mu epsilon dou square E by dou T square, and del square D is equal to mu sigma dou D by dou T plus mu epsilon dou square D by dou T square. Likewise, there are four equations here, four equations drawn from Maxwell's four equations, and this is a general wave equation which will vary with respect to this time in second order. Okay. Now continuation with this uniform plane waves, you could see in free space, what happens in free space? In free space, conductivity will be equal to 0, that is sigma is equal to 0. Therefore, E, that is electric field, will be in x direction only. Electric field will be in x direction only, whereas H will be in y direction only. Okay, so E is in x direction and H is in y direction. E and H does not vary with respect to x and y. Remember, E and H will not vary with respect to x and y coordinates. Seems to be parallel, but vary with respect to z and t. But vary with respect to z and time. See here, this is varying with respect to z, and you could remember that time varying electric field produces what? Produces time varying magnetic field, right? And these two are perpendicular. So here, if this is H and this is E, next direction, so this is varying with respect to time, and the wave is propagating in Z direction. So this E and H varies in terms of Z and T only. So this is very important concept here before we go to the next topic. E and H are mutually perpendicular to each other, and E and H will not vary with respect to x and y, but varies with respect to Z and T. Therefore, E and H are mutually perpendicular to each other. E and H are mutually perpendicular to each other, and EM waves are called transverse EM waves, and hence this kind of electromagnetic waves are known as transverse. Transverse EM waves. Therefore, I can write the equation for E, that is electric field, for EMW or electromagnetic waves as E is equal to Ex is a function with respect to Z and T in the direction Ax. So what is E is equal to? Electric field is the function of Z and T in the direction Ax, and similarly H, that is magnetic field, is a function of Z and T. Sorry, this is not Hx now, this is Hy of Z and T in the direction Ay. Okay. So now consider the wave equations for E and H. See here, I'll consider the wave equations here I'll consider del square E and del square H. I'll consider these two equations here also. This and this here also with respect to electric field and magnetic field. So consider wave equations for E and H can be given by, I'm trying to derive the wave equations for uniform plane waves. Del square E is equal to mu sigma dou E by dou T plus mu epsilon del square E by dou T square. Call this as equation 1. And del square H is equal to the same coefficients, mu sigma, but dou H by dou T plus mu epsilon dou square H by dou T square. Call this as equation number 2. So as we know, for free space, sigma is equal to 0 and epsilon is equal to epsilon naught, mu is equal to mu naught. So this electromagnetic waves is assumed to be traveling in free space. So in this situation, sigma is equal to 0, epsilon is equal to epsilon naught, mu is equal to mu naught. Therefore, equation 1 and 2 can be rewritten as del square E. Now it will be left with only second order derivatives. Del square E is equal to mu naught epsilon naught dou square E by dou T square. Call it as equation number 3. Del square H is equal to mu naught epsilon naught dou square H by dou T square. Call this as equation number 4. Okay. So I could write this left hand side equation del square E. So what is del square E, guys? So based on your Laplace equation, so del square E will be equal to so dou square E by dou x square plus dou square E by dou y square plus dou square E by dou z square, right? So what is a del operator? If you have forgotten, so what is del operator? Del operator is equal to dou by dou x in the direction ax plus dou by dou y in the direction ay plus dou by dou z in the direction az. What is del square E then? So it will be dou square E by dou x square plus dou square E by dou y square plus dou square E by dou z square. But wave travels, and this is equal to the right hand side equation is equal to mu naught epsilon naught del square E by dou t square. But what happens with respect to this del square E? But wave travels only in z direction. So the wave travels only in z direction. So I will retain only z component. Therefore, dou square E over dou z square is equal to mu naught epsilon naught dou square E by dou t square. Okay. Again, but E has what? E has only x component, right? E has component only along x direction. So I can represent this E as Ex. Similarly, H as magnetic field is in the direction Hy. I represent it in terms of Ex and Hy. Therefore, and also E and H, remember E and H are functions of only Z and T. Why? Because wave traverses only in Z direction and will vary with time. So E and H varies with respect to Z and T only. So I can write the above equation as, I'll write this equation, let me represent this as equation 5 and this as equation 6. I can write equation 6. Therefore, equation 6 becomes dou square Ex by dou z square is equal to mu naught epsilon naught dou square Ex by dou t square. We'll call this as equation 7. Call it as equation 7. So now, what is Ex? Ex is a function of Z and T. So let Ex be the value varying with respect to exponentially or sinusoidally. E is equal to Em e to the power of j omega t, where Em is some amplitude of electric field. Em is some amplitude of electric field and omega is angular frequency. So now I say E is varying with respect to Em e to the power of j omega t. So in order to equate or in order to satisfy this equation 7, so what I'll do, I'll partially differentiate this equation twice with respect to t. So I'll be differentiating Ex with respect to t before I substitute to equation 7. So what happens if I take the partial derivatives of second order with respect to t? So this will be dou square Ex by dou t square is equal to Em is constant, j omega into j omega 2 times we have differentiated of e to the power of j omega t, which will be equal to minus omega square Ex e to the power j omega t, because J is equal to square root of minus 1. J square is equal to minus 1. You could see why did you get this minus 1? Because J square omega square. So omega square is retained as it is. So J square is equal to minus 1 e power x. Sorry, this is EM, right? EM e power j omega t. But we know that e power m, sorry, EM e power j omega t is equal to what? EX. So this coefficient will be equal to what? EX. Therefore, I can write this equation as dou square EX by dou t square, which is equal to minus omega square EX. Call this as equation number 8. And now substitute this equation 8 in equation 7. So what happens if I substitute equation 8 in equation 7? I will get dou square EX by dou Z square is equal to mu naught epsilon naught of minus omega square EX, which is equal to minus omega square mu naught epsilon naught EX, and call this as equation 9. Guys, I'm audible?
Yes, sir.
Okay, fine. So now I'll say I just want to represent this ninth equation in terms of some linear equation. So let with simple terms, dou by dou z equal to d. So let first order differential equation with respect to dz can be represented as d. Therefore, dou square by dou z square can be represented as d square. Therefore, equation 9 becomes d square ex minus omega square mu naught epsilon naught ex. So this is equal to minus. Okay. So now I can rewrite this equation as d square ex plus omega square mu naught epsilon naught ex is equal to 0. Therefore, the auxiliary equation becomes, so this is an auxiliary equation, it becomes d square plus omega square mu naught epsilon naught times ex is equal to 0. Therefore, d is equal to minus omega square mu naught epsilon naught. Therefore, this is d square, right? Therefore, d is equal to plus or minus square root of excuse me, plus or minus square root of minus omega square mu naught epsilon naught. I can represent this minus in terms of j square, right? So I can represent this minus 1 as j square omega square mu naught epsilon naught. So this is plus or minus d is equal to. Therefore, I can bring this j square omega square term outside, plus or minus j omega square root of mu naught epsilon naught. So d is equal to plus or minus j omega square root of mu naught omega naught. But you could see phase shift constant can be represented as omega square root of mu naught epsilon naught. Therefore, d is equal to, sorry, this is not a vector, it's a constant. D is equal to plus or minus j beta. So what is this beta? Beta is a phase shift constant in radian per meter. So where beta is equal to omega square root of mu naught by epsilon naught, where air as a medium, in general beta is equal to omega square root of mu epsilon in general, and this is called as phase shift constant. So you might get a question like obtain a phase shift constant of a uniform planar waves. So this might be one question that what you can expect. So you want this equation to be obtained from the uniform plane wave equation, followed by I've not yet obtained the general wave equation in time domain or uniform plane waves. So here, if you look at the equation number 9, what is equation number 9? So equation 9 was this. Okay. So if you look at this equation 9, so equation 9, the solution of equation 9 by taking the integral form and all. So there is no simplified form here. So you could directly write, hence, because this derivation is already a lengthier, we could just try to reduce the effort here. Hence, the solution of equation 9 can be written as Ex is equal to, since you had second order differentiation, you will get two constant C1 and C2 if you integrate it twice in terms of e power minus j beta z e power j beta z. So this would be the solution of equation 9 if you take the integral of equation 9 two times, but let C1, the constant, is equal to Exm, and C2 is equal to Exm dash. Therefore, I can write the equation Ex is equal to Exm e power minus j beta z plus Exm dash e power j beta z. So this is a very crucial equation. This you have to memorize this, because there is no solution been derived by substituting or subjecting equation 9 to integral parts. And this is the general wave equation in phasor form. This is the wave equation, very important question, wave equation for uniform planar waves in phasor form. In phasor form, where beta is a phase constant. to obtain wave equation in time domain. Remember, note to obtain the wave equation in time domain, multiply phasor form with e power j omega t. You have to multiply equation 10. You have to multiply equation 10 by the phasor form, that is e power j omega t. Therefore, multiplying equation 10 by e power j omega t, you would get Ex. Now Ex will be in terms of time domain. Now Ex is a function of z and t, which is equal to, and consider only the real part here, multiply with e power j omega t and take or consider real part of it. Real part of it after multiplying. This is very important. So in order to obtain the wave equation in time domain, you have to multiply it by e power j omega t and take only the real part. So e power ex z comma t will be equal to real part of e xm e power minus j beta z plus e xm dash e power j beta z. Now you multiply this with e power j omega t and take the real part of this. You would get the final equation, wave equation for uniform plane waves in time domain as Ex z comma t is equal to Exm cos of omega t minus beta z. See here, this is e power minus j bz, e power j omega t would be omega t minus beta z of j, correct? And the real part is cos of omega t minus v beta z. So e power j omega t would be equal to cos of and then plus sine of omega t minus v beta z plus j sine theta. So e power j theta can be expressed as cos theta plus j sine theta, and I will represent only real term here. So the real term of this multiplication factor will be Ex of z comma t equals Exm cos omega t minus beta z plus similarly Exm dash cos omega t plus beta z. See here, this term. Now this equation is the final wave equation of uniform plane waves in time domain. And the first half, that is Exm, is known as forward traveling wave. Forward traveling wave, and this coefficient of xm dash is called as backward traveling wave. And this is the equation for E. Similarly, you can write the equation for Hy, that is magnetic field, varying with respect to Z and T only, as Hym cos of omega t minus beta z plus Hym dash cos of omega t plus beta z. This is H equation in time domain. So you need to remember this derivation. Here the solution of equation 9. So this is one crucial step, and then say C1 is equal to constant and obtain this. This is a phasor form. Equation 10 is a phasor form. To obtain in time domain, so it should be a real part. After multiplying this phasor equation with e power j omega t, extract only the real part. So you'll get only the cos terms here, because e power j theta is equal to cos theta plus j sin theta, and this cos theta is the real part. And considering only the real parts, in order to obtain the time domain equation for electric field for uniform planar waves equation in terms of forward traveling wave and backward traveling wave is given by this equation. Similarly, I can draw Hy in time domain, the equation for uniform plane waves in time domain. So these things you need to remember while deriving the equation for uniform plane waves for E and H. So you might get a question, derive E and H equation for uniform plane waves, or derive uniform plane wave equations, or derive phasor equation or phasor constant for uniform plane waves, which will be in terms of beta is equal to j square root of, what was the phasor constant? Beta is equal to omega, or j square omega mu epsilon. Hope you got it. If you understand this, otherwise you have to watch this video a couple of times, and then you have to make your own notes, which equations you could understand, which equations you are feeling it difficult to understand, that you have to memorize, because there is no detailed derivation for you guys. This is all, this itself is a very big derivation already. There is no detailed derivation, just you need to remember how did you got that solution of equation 9 in terms of C1 and C2, EXM and EXM dash. So that part, if you remember, the rest of the things is very simple. And the final equation is very important. This equation is very important. How did you get this equations of E and H in time domain? Because you multiplied equation 10, that is phasor form of equation, by e power j omega t, and you have considered only real point or real part of it. Is that okay? So in the next class, we shall discuss about the relationship between E and H in free space and Poynting's theorem. We also have wave parameters. Yeah, wave parameters is also there. We shall discuss with wave parameters. Intrinsic impedance, wavelength, phase constant, propagation constant. There are some parameters of wave, some simple definitions that you need to remember, and then we shall try to obtain the relationship between E and H. So E and H is related. E and H is equal to eta naught. So you might get this. So prove that E and H, E over H is equal to eta naught. So that we shall derive in the next class, followed by, so eta naught or eta is called as intrinsic impedance. And followed by Poynting's theorem. So please attend to the next class. Why? Because this is very important theorem. So it is drawn from your Maxwell's equation. So we'll start with Maxwell's equation and obtain Poynting's vector or a Poynting's equation in terms of energy coefficients, like half mc square, in terms of half mc square, or in terms of half xy square. So we'll start with Maxwell's second equation and we shall obtain Poynting's vector and Poynting's energy equation to understand what happens with respect to the EM wave while propagating or while traveling in free space. What happens to the power in terms of energy and impedance. So in order to understand power in terms of energy and impedance, we need to understand the wave parameters like propagation constant, impedance, and intrinsic impedance, propagation constants, wavelength, and anything else. Yes, velocity of wave. C. So there are some parameters which could be used to define a wave. Here it's an electromagnetic wave, and then we shall try to obtain impedance equation in terms of E over H, and then we shall obtain Poynting's theorem. So these are the three concepts which has been left in your electromagnetic wave theory. Hope you understood this derivation for E and H fields in uniform plane waves. You can also say uniform plane wave equations for E and H in time domain. If you have any doubts, just let me know.